Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Discontinuity Layout Optimization, and it is going to provide you the mathematical formulations and also the work problem. I am going to give you an overview of what I am covering in today's video. First at all, it is an introduction of layout optimization, and then focus on the mathematics and the simple example before wrapping up with conclusions. While finite element analysis is traditionally concerned with formulation and solution of a continuum mechanics problem, it is alternatively possible to consider a potentially similar discontinuous problem. This involves directly identifying the discontinuities which form at failure. However, previous attempts to develop discontinuous limit analysis formulations have been largely unsuccessful, because previous formulations have permitted a limited range of possible failure mechanisms to be considered. In fact, a successful discontinuous limit analysis procedure must be able to identify the critical arrangement of continuities from a wide, preferably near infinite, number of possibilities. With this in mind, an alternative approximation procedure to the traditional finite element method might involve discretization of a given planar body using a suitably large number of nodes laid out on a grid, with the failure mechanism comprising the most critical subset of potential discontinuities interconnecting these nodes. Posed in this form, the problem is now strikingly similar to the problem of identifying the optimum layout of discrete bars in chassis. We now begin by exploring the nature of the analogy between optimum chassis and optimum layouts of discontinuities, focusing particularly on approximate discretized formulations which can be solved using linear programming (LP). In the layout optimization of chassis, we consider a planar design domain which is described using n nodes and m potential connections. The minimum volume Chassis formulation is very similar to the Chassis analysis formulation. However, the objective is now to maximize the volume or weight of the structure, rather than to maximize the load factor lambda. Since the applied loads are fixed in the design problem, the equilibrium constraint is written as B times Q equal to F. Also, the cross-sectional areas of the members are not fixed, and become additional problem variables. We also set up yield constraints. Finally, the objective function is to minimize the total volume. Now we are looking at a very simple example. If we have a design problem where we've got a design space showing right-hand side of the screen, we don't know how to arrange the members. The first thing we do is we arrange design space with nodes, and then connect those nodes with potential members and potential chassis bars. We use optimization to find the minimum volume subset of members forming optimal solution. In the DLO, the kinematic slip line discontinuity layout optimization formulation for the plane strain analysis of a quasi-statically loaded, perfectly plastic cohesive body discretized using m-nodal connections, n nodes, and a single load case. Similarly, the equilibrium constraint becomes B times D equal to U. Also, the displacements of the discontinuity members are not fixed, and become additional problem variables. We also set up yield constraints. Finally, the objective function is to minimize the total internal energy dissipated due to shearing along the discontinuities. Now we are looking at a very simple example. If we have a block of soil on right-hand side screen, with the fixed boundaries to the left and the base, load at the surface, instead of populating with elements of finite element approach. In this approach, we do populate the debate with nodes. And essentially, we connect every node to every other node with a potential slip line. So here, we've got 12 nodes. There are 12 times 11 equal to 266 connections that we use optimization to pick out of that set of potential slip lines, the critical ones that form the critical collapse mechanism. The analogy between chassis layout optimization and plane strain limit analysis problems has now been demonstrated. The DLO procedure generates a kinematically admissible discontinuities velocity field or compatible rigid block mechanism, which represents a valid upper bound solution according to the theorems of plasticity. However, it should be borne in mind that the direct analogy with transfer optimization applies only when translational failure mechanisms and a weightless cohesive trace-car material are involved. While attention will be limited to translational failure mechanisms in this video, there is a clear need to treat other common constitutive models, the more Coulomb failure criteria, and also to be able to include self-weight. Furthermore, it is not especially convenient to specify external loads and other boundary conditions in terms of nodal displacement. A more convenient and potentially powerful revised limit analysis formulation will be discussed. The contribution of each potential discontinuity to the global compatibility constraint equation can be written as B times D equal to U. Alternatively, this can be expressed in expanded form for a cohesive trace-car material as this matrix, where alpha and beta are the x-axis and y-axis direction cosines for discontinuity, connecting nodes A and B respectively, and the actual shear displacement at the discontinuity S equal to S plus minus S minus. Now consider a cohesive frictional material governed by the more Coulomb failure criteria. In this case, the associated flow rule can be written as N equal to S times tan phi, where phi is the angle of friction, dilation, and N is the normal displacement accompanying the sliding. Since this equation stipulates that the normal displacement N is simply a linear function of the shear displacement, this means that a combined compatibility and flow matrix can be derived and used when a cohesive frictional soil is involved. Thus, the equation of B times D equal to U can be replaced with a new combined compatibility and flow constraint. However, the linear dependence of the normal displacement on the shear displacement makes this a rather special case. If more complex yield criteria are involved, if a notation condition were to be added, then it becomes necessary to adopt an alternative approach. Thus now, using LP variables S and N in D to represent respectively the shear and normal displacement at discontinuity, the local compatibility and the flow rule constraints are shown in the right-hand side of the screen. In the previous DLO problem formulation, the objective was to minimize the internal energy E. This also leads to the minimization of the work done by the external live loads. However, in many problems, dead loads including body forces are also present, requiring that additional terms are added to the work balance equation. Thus, an expanded work balance equation may be written as the first equation in this screen. It is convenient to distinguish between loads applied at external boundaries and those applied within a body itself. For dead loads applied within a body, the contents of Fg can be obtained by summing up the total overlying dead load, excluding boundary dead loads. Consider, for example, a problem where the dead load results solely from self-weight effects. Here, the contribution made by discontinuity to the transpose Fg times D term can be written as this matrix. This action of this equation is illustrated in the right-hand side screen. Consider any vertical strip of a problem domain that doesn't contain any nodes or crossovers such as AIJB, and further consider that only slip line CD is active. It can be seen that the vertical component of any movement on slip line CD will result in work done against the gravity equal to the mass of area EIJF. We will now have an additional vertical movement relative to that computed previously for area CIJD. For the live loads, taking U equal to 0, all live loads can be specified by imposing the following unit displacement constraint: transpose FL times D equal to 1. Now we can revise LP formulation. I revised the primal kinematic problem formulation for the plane condition analysis of a quasi-statically loaded, perfectly plastic cohesive frictional body discretized using M-nodal connections, slip line discontinuities, N nodes, and a single load case can be stated as these formulations. Next, we will analyze a simple example. A simple wedge collapse problem using 4 nodes is initially with full calculation presented. A simple problem is considered, with a load applied on the top face, with the right face free and all other faces fixed. Potential sliding failure mechanisms for unit displacement enforce that the discontinuity of the applied load on the edge C. Failure mechanism is not possible for non-compressible soil where it is restricted by the rigid edge D. Hence, Figure B represents the plausible failure mechanism. And for a unit displacement in the direction of the applied load, the soil block shown in Figure C shows slide a value of D equal to 1.414. According to the external work done equal to internal energy dissipation, we can calculate the critical load as 2. Now we can use the automatic DLO method to solve the same simple wedge collapse problem. Before set up the computing equations, we need to introduce 4 boundary conditions. The first one is rigid. Both shear and normal displacements are allowed along with energy dissipation, with values of cohesion C and angle of friction phi, and where the associated flow rule applies. For the symmetry plane, it allows only for shear displacement, but no normal displacement and no energy dissipation along the edge. In a free edge, both normal and shear or slip displacements are allowed. While there is no energy dissipation, the flow rule here doesn't apply, leaving the shear and normal displacement to be unrestricted. For the flexible load boundary condition, the loads can move with the discontinuity, and if the load is applied along several discontinuities, then the discontinuities can move independent of each other. There is no energy dissipation between the surface of the body applying the load and the discontinuity. Now we can set up these boundaries in our calculation. In this case, there are 4 nodes and populate 4 times 3 equal to 12 discontinuity elements. Each discontinuity has the relative boundary constraint. The equality matrix can be created, which includes all the conditions that the objective function is subject to, the compatibility condition, the flow rule, and the application of a unit load. The equality matrix is multiplied by a vector of LP variables that accommodates vector D of relative displacement of discontinuities and vector P of the plastic multipliers. Finally, we can obtain the failure mechanism of this simple example, and the critical load factor is 2, which is the same with our hand calculation. From conclusions, what we learned: the analogy between approximate discretized formulations for Chart layout optimization and slip line discontinuity layout optimization has been established. Discontinuity layout optimization provides a new and highly efficient tool for geotechnical engineers, effectively automating the traditional upper bound hand analysis method for the first time. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,